Let's start with number 69 on page 330. It says find the derivative of the function. We have f of x equals the integral of. Okay, so it's a function defined as a definite integral, and we're going to find its derivative. What theorem are we going to use? Second fundamental theorem of calculus. So we've got f of x defined to equal the definite integral from 2 to the natural log of 2x of t plus 1 dt. So according to the second fundamental theorem of calculus, whenever you have a function defined as a definite integral, and the lower limit of integration is a constant, and the upper limit of integration is either x or an expression of x, that we can find the derivative very easily. If it was just an x as our upper limit of integration, our derivative would be x plus 1, wouldn't it? Okay? But it's not. It's a u. It's a natural log of 2x. So remember how that one works. It's a chain rule version of the second fundamental theorem of calculus. So we'll get f of u times the derivative of u. So our derivative, f prime of x, equals f of u. So in that parentheses there, that's f of u. That's putting u, the natural log of 2x, in for t. So the natural log of 2x plus 1, that's f of u, times the derivative of u. So now we have to take the derivative of the natural log of 2x, which we couldn't do until we got to this section. But now we can. The derivative of the natural log of 2x is 1 over 2x times the derivative of 2x. Different u, but the derivative of the natural log of u is 1 over u times the derivative of u. So 1 over 2x times the derivative of 2x. Well, then you simplify as much as you can. So the 2's here divide out. And then if you want to write it as one expression, that's good too. And just for fun, that's how we would do it if we didn't remember how easy the second fundamental theorem of calculus works out. I'm still using the second fundamental theorem of calculus, but I wrote out the substitution. I figured out what du dx was separately ahead of time. I wrote the chain rule over here off to the side. But, you know, over the years, I've decided just remember how it works. Okay? That's how it works. Any questions on this one? Okay. And we'll start with number 23 then. All right, here's 23. What do the directions have us do? Find the derivative. I expand it. That's even better. So use the properties of logarithms to expand the logarithmic. So first, I'm going to change radical notation to exponential notation, and then use your exponent property of logarithms to make that 1/3 times the natural log of a squared plus 1. And look, that's as far as you can go. Fairly common mistake, but one that you really need to not make is this. That's a misuse of the product property, isn't it? Yeah. Okay? So be careful. You cannot do that. So that's as far as I can go with 23. I don't know what you mean. All right, 37. This time the directions say to find the limit. All right, so we have the limit of the natural log of x minus 3 as x approaches 3 from the right. And the from the right actually matters, doesn't it? Because if x approached 3 from the left, then the expression inside the parentheses would be negative, and the natural log does not exist for negative numbers. Okay? Now, reason it out here. Isn't that a logical conclusion that those two things are the same limit? Because what's happening inside the parentheses as x approaches 3 from the right? The expression inside the parentheses is approaching 0 from the right, isn't it? So I just rewrote it like that. Can I do that? They're logically equivalent, so why not? Okay? And then once I've got that, remember how you're supposed to have a notion of what the natural log function graph looks like? So, as x approaches 0 from the right, where's the y-coordinate going? Negative infinity. Okay? What else? 55. All right, what are we doing here? State of the function. All right, on 55, we have the natural log of the natural log of x squared. Now, this expression in the parentheses, the natural log of x squared, I use the exponent property that we know for logarithms to make that 2 times the natural log of x. And then I think I can pull it off from here. So think of that, all of that as being the u. So the derivative, so y equals the natural log of u. So the derivative of the natural log of u is 1 over u times the derivative of u. So 1 over u times the derivative of u. All right, so what was u? 2 natural log of x. So 1 over 2 natural log of x times the derivative of u. What was u? 2 natural log of x. So times the derivative of 2 natural log of x. Constant multiple rule will be 2 times the derivative of the natural log of x. What's the derivative of the natural log of x? 1 over x. Follow me on all that? Then we can divide the 2's out. So you get 1 over x over the natural log of x. That's no good. Multiply by x over x, and you get 1 over x natural log of x. That makes sense? I saw a lot of confused faces on that. Questions on this one? '52 is a whole other story. And we'll see. All right, on 52. I'm going to use my logarithm properties to make this a tad easier. So I'm going to rewrite the natural log of 2x over x plus 3 as the natural log of 2x minus the natural log of x plus 3. And then finding the derivative of each of those two terms is easy. Each one of those is easy. So for the derivative of the natural log of 2x, I'll get 1 over 2x times the derivative of 2x. You see how that's 1 over 2x times the derivative of 2x? All right, then a minus sign, and the derivative of this of the natural log of x plus 3 will be 1 over x plus 3 times the derivative of x plus 3. Make sense? Okay. Well, I don't know why I didn't divide those 2's out. Yeah, I guess I wanted to make my work harder. So I went ahead and got a common denominator. which means I need to multiply the figure, the fraction on the left by x plus 3 over x plus 3. And then since I didn't divide those 2's out like I should have, I got to multiply the fraction on the 2x over 2x. Do a little multiplying. Common denominator means I just add the numerators together over my common denominator. And then finally, I had enough sense to divide the 2 into the 6. 52 makes sense? All right, Joseph, did you ever figure out what you were wanting to ask me a minute ago? Okay, so I moved the 3 in front using the exponent property. Then leave the 3 out in front. The natural log of that quotient will be the natural log of the numerator minus the natural log of the denominator. Okay? And on this particular one, I can factor that. Now, normally, like if that was x squared plus 1, that's not factorable. That's what I would be left with. Okay? Because there's nothing else I can do. But x squared minus 1 is factorable as x plus 1 times x minus 1. So that's the reason I could then make it the natural log of the first one plus the natural log of the second one. Okay? The fact, and it's not going to come up all that often, but the fact that that's factorable lets me do that and then that. Okay? If the very first thing I highlighted was not factorable, then I would be finished with that. I wouldn't be able to do anything else to it. Yeah. Here's the thing. If you've got the only thing you can do, if you've got the natural log of a quotient, we can expand it. A product, we can expand it. An exponent, we can expand it. Otherwise, no. All right, what else? Any others? No rules at all for adding or subtracting. Okay? That's the reason, like, now, well, I take it back. I mean, we can go backwards, right? We can group those together and turn it into a product. Then we can group those together and turn it into a quotient. But as far as expanding goes, no. All right, Lindsay? 36. All right, what are we doing on this one? It says verify that f equals g by using a graphing utility to graph f and g in the same viewing window. And then, so you can do that. And then verify, oops, I lost my place. Then verify that f equals g algebraically. So that's what we're going to need to work on here. So f of x equals the natural log of the square root of x times the quantity x squared plus 1. G of x equals 1/2 times the natural log of x plus the natural log of x squared plus 1. Now this is a lot like when you were working with trig identities previously. You can really work with either one. You can work with both and then have them meet in the middle. It doesn't matter as long as you can prove that they're equal to each other. So what I did is I just dealt with f of x. I changed the radical notation to exponential notation. Then I changed the exponent to a constant factor in front. All right? So already I've got that now, right? So then I need to try to expand the natural log of x times x squared plus 1, which I can. I can make that the natural log of x plus the natural log of x squared plus 1. And then you look and you see, oh, that's what I was trying to do. Yeah. I don't know what you mean. Like multiply the x times the x squared plus 1? Probably not. You can, but then you can't expand it anymore. And expand, especially if expansion, let's put it this way. There's a lot of benefits to expanding it. So is there some time where we would want to turn that into 1/2 times the natural log of x cubed plus x? Maybe. You can do that. It's perfectly valid to do. Yeah. 26. All right, we expand it again. All right, so we've got the natural log of 3e squared. So first we use the product property to make that the natural log of 3 plus the natural log of e squared. Exponent property, leave the natural log of 3 alone. It's fine. There's nothing else we can do to it. But the natural log of e squared, use your exponent property, make that 2 times the natural log of e. And then almost always we would be done there, wouldn't we? But what they've done to us this time is they've given us an expression we know how to simplify. The natural log of e equals 1. That's what e is defined to be. It's the number whose natural logarithm equals 1. So replace the natural log of e with 1, and then 2 times 1. Okay? So when you get the natural log of e, replace it with a 1. When you end up with the natural log of 1, you should replace it with? Nope. What's the natural log of 1 equal? 0. So those are the 2 times when you'll take a natural logarithm expression and replace it with a number. The natural log of e equals 1. The natural log of 1 equals 0. Okay? Others? Yeah. 30. All right, so now we're going backwards, right? They give us something all expanded out, and they tell us to write this as the natural log of one expression. Is that how they say it? Of a single quantity. Okay, one expression. So, first, use your exponent property backwards to turn that into the natural log of x cubed, turn that into the natural log of y squared, turn that into the natural log of z to the 4th. Don't change your plus signs and your minus signs. Now, these have a plus sign between them, so I can use the product property backwards to make that the natural log of a product. I didn't mess with the natural log of z to the 4th. And then now, these have a minus sign between them, so use the quotient property backwards to turn it into a quotient. Alrighty? 61. All right, on 61, we're supposed to find the derivative of the function. So y equals negative square root of x squared plus 1 over x. We've known how to do that for a while, haven't we? Okay? So we should be good there. Now, notice this. I did take that negative sign and kind of think of that as a negative 1 times using the constant multiple rule. Then I'm using the quotient rule. The bottom, x, times the derivative of the top. And look, all of this is the derivative of the top with the chain rule, right? Think of that square root as a quantity to the 1/2. So 1/2 times u, subtract 1 from the exponent, times the derivative of u, and then finish off the quotient rule. Minus the top times the derivative of the bottom, the derivative of x is 1, over the bottom squared. We good with the quotient rule, with the chain rule inside of it? All right, now, our second term is the natural log of x plus the square root of x squared plus 1. And even though we just spent a bunch of problems before we get to this one, expanding using logarithm properties, and all that, we can't expand that one, can we? Okay, it's not a product, it's not a quotient. So, the derivative of the natural log of u is 1 over u times the derivative of u. So, 1 over x plus the square root of x squared plus 1. I did change that to exponential. Exponential notation, but that's the 1 over u part times the derivative of u. Well, the derivative of x is 1. The derivative of the square root of x squared plus 1. Well, hey, didn't we do that already? Like over here? So it's the same thing again, using the chain rule. So exponent in front, u, subtract 1 from the exponent, times the derivative of u. So before we move on, you guys follow me that far? Okay. Now, I'm not positive at this point that I'm going to be able to take that and get one fraction out of it, but that's what I need to try to do, isn't it? Okay? So keep that in mind, that what I'm going to need to try to do is get one fraction out of this. That's going to affect my thinking on what I want to simplify. So I'm looking, and I'm seeing that as a denominator, and then, oh gracious, that is a denominator. All right, okay. Oh my, negative, and a, okay, so we got a work cut out for us. Let's go a little bit at a time. Let's take in front of the plus sign first, okay? So here, I've got a negative exponent there as well. I'm not wanting to end up with a negative exponent now, okay? But I can't just move that expression to the bottom because it's not a factor. It's times the 2x, and it's times all of that, but it's not times that, is it? So it's not a factor. I can only switch from top to bottom because of negative exponents when it's a factor with a negative exponent. Well, guess I'd better factor then, hadn't I? So what I've got to do then is factor. So I've got an x squared plus 1 and an x squared plus 1 that I'm going to factor out as a common factor. Okay? Oops. 1/2 times 2 is 1. Got rid of that. So I've got my negative sign in front. I've got x times x. That's x squared. And then I've got a factor. Well, that's all I did in this step, isn't it? Then I've got almost a factor of x squared plus 1 to the negative 1/2. Then I've got this expression of x squared plus 1 to the positive 1/2. So now I factor. The negative stays in front. I've got a quantity. It's the exact same quantity in both circles with different exponents. So when I factor that quantity out, always take the lesser exponent. So since one of them's positive, one of them's negative, the negative one's the smaller one. So use the negative 1/2. And then look, it works out really nice after that. I know you guys don't really like this a whole lot, but it does. It works out really nice because that divided by itself is 1. So what am I left with in the parentheses? X squared times 1, which is x squared. Copy down the minus sign. And then look, this divided by the same expression with a different exponent. When you divide factors with the same base, you subtract exponents. 1/2 minus negative 1/2 equals, not 0, 1, right? 1/2 minus negative 1/2, 1. So it's the quantity with an exponent of 1 on it. You following me? So we're all to here. Right now, look what I can do. Now, that's a factor. So I can take that factor to the denominator, make the exponent positive. So it's not there anymore, it's there. And in the parentheses, distribute this negative so you get x squared minus 1. Well, in my world, x squared minus x squared is 0. Leave me with that negative 1. Okay? All right, now, I've got a negative in front of my whole expression. What's negative 1 times negative 1? And that's what I get when I simplify the fraction in front of the plus sign.
So with basically would you recommend simplifying first and then try to manipulate the equation?
You've got to do at least some simplifying first. If I don't deal with this, then I'm never going to get to a good answer. So what my concern was for all those steps was getting rid of that negative exponent. Okay? Now once I'm here, then I'll worry about getting a common denominator. But if I never got rid of that negative exponent, I'd be wasting my time anyway. Okay? All right, so we come back over here to here. All right, and let's see, what did I do here? All right, I've got a negative exponent, don't want it, but look, I've got a problem. I can't simplify this one the way I did the other one that I just finished, can I? Because I don't have that x squared plus 1 with a different exponent on it also in the numerator. So here's what I'm going to do instead. All right, first I'm going to multiply that 1/2 times that 2 and get a 1. So I've got 1 plus, and then all I have there is a factor of x. Then I've got that thing with the negative exponent. I'll leave the denominator alone. Okay? So then the question becomes, since I can't factor out an x squared plus 1 to the negative 1/2, how can I get rid of it? Well, I can turn an exponent either positive or into a 0 by multiplication, because when I multiply factors with the same base, I add the exponents. So if I multiply by the base I want with an exponent of 1/2, what's going to happen when I do that multiplication? What exponent am I going to end up with? A 0. Is that good? Yeah, it is. Okay? So that's why I decided to multiply by x squared plus 1 to the 1/2 to the 1. Okay? Now, when I multiply that times 1, I get that. When I multiply that times this, when I multiply those two factors with the same base, negative 1/2 plus 1/2 is 0. What's that expression with an exponent of 0? 1. So times a 1, and what the only thing I have left is an x. X times 1, x. Well, that was nice. Don't look at the denominator, and you'd be very pleased at this point, right? But we do have to look at the denominator. All right, so I've got my original denominator times that new thing that I decided I needed to multiply by. Okay. And let's see, what did I do here? No. That is what I did. You said cross out, and it made me nervous. Because when I hear students say cross out, what I see in my mind is, ooh, I can do that, and I can do that. I can get rid of that with that. We'll pretend that's not there. I thought that's what you were doing. No, that's right. All right, what's in the red parentheses? Those are the same thing, right? One way it's written A plus B, the other way it's written B plus A, but same thing. So I can divide those out, because anything divided by itself is 1, leaving me with 1 as the numerator. Then this nice little x squared plus 1 to the 1/2 is the denominator. All right, so it's time to start trying to put these together. Y'all be quiet. So I need to be able to combine those. They almost have the same denominator. The one on the left just has an extra x squared in there. So I multiply by x squared over x squared to get x squared over x squared times x squared plus 1 to the 1/2. Now we have the exact same denominator for each fraction, and you can combine the numerators over your common denominator. Oh, so that was easier than I thought it was going to be.
Problems like that on the AC test?
Oh, yeah. To warm up on? Yeah.
Oh, I have a question about, on Saturday, what time do you think we'll be done?
We'll talk about that in a minute. All right. We need to do page 330, 63 through 72, and 101 through 104. Depending upon what academic year you're watching this video, you may have already been assigned those. Maybe you haven't. Either way, that's what you're doing now.